Okay, we're going to do a couple more examples of the synthesis and reactions from the homework sheets that I gave out that are online. So we're going to try this one up here and take a look at how to do that. So first thing I need to do is recognize this is an alkane. There's no real functional group on it. These are apparently the materials that are going to react with it, and so I'm going to go and try and find it out. Similar for any one of these, I got to identify essentially what this is. So there's an alkene here, so this is a reaction of an alkene. This is a reaction of an alkane. Once again, another alkene. This is a reaction of alkene. And if I were to keep scrolling down, reaction of an alkyl halide, reaction of an alkene, reaction of an alkyl halide. But note that there's two on adjacent carbons here. That might be something special. It is. Reaction of an alcohol and reaction of halogen or alkyl halide again, but note that these are on the same carbon here. Okay, and so what we do then is we try to look up the reagents as in relationship to the functional group that we're trying to deal with. So we'll do a couple of these and see how they go. So we'll start with this one up here. So when I look up in the summary from Wade that I've got, we can see that under reactions of alkanes, that this is a generic carbon here attached to a hydrogen. And so under these conditions, I can have chlorine, bromine, or iodine. And using either heat or light, I'm going to be able to replace a hydrogen with that halogen. So that's essentially the reaction we're looking to do. So the HV that we see on the other side is actually another term for light. So HV is energy, and this light is in units of energy, or in terms of energy would be shown as HV sometimes too. So many, many different forms. So an example here is this compound where we've got a hydrogen hanging off. Any one of these hydrogens actually could react, but specifically they're only showing this one. So they're having the bromine be replaced. So there's a carbon-hydrogen bond, and this hydrogen is replaced by a bromine. This hydrogen is replaced by a bromine, one bromine, not two of them, but one. All right, and so what they don't show is the byproduct. So over here, they do show that there would be the extra hydrogen that got removed and the extra halogen that was here. They form together. But most of the times in organic chemistry, they don't show byproducts. They only show the major product. So the questions that I got in the video, in the quiz, essentially tell you to name the major product and name it with a IUPAC ruling. So this is what the compound looks like. There's our three carbons. What I've done is I've extended out the hydrogens that were involved. And just note that there's three hydrogens here, but any one of these can be picked off by the bromine. It's not very selective. It's more based off of statistics. So there's three hydrogens here, there's only two here and three here. These sides are essentially equivalent, so there's 6 times more chance that it's going to get here than the 2 times here. So it's a 3-to-1 ratio that they're going to hit out here. But in the quiz, I've got both answers. So we're going to brominate one of these hydrogens, and as another example, we'll brominate one of these, and we'll see the two different answers that are associated with it. So for the first one, I'm going to retract a bunch of the hydrogens, but essentially I'm going to brominate, we'll brominate this one here for the first one. And so what I'm going to do then is I'm going to have bromine hanging off. And so there it is. That's our final compound, and we just need to name it. But I'm going to also name a different one. So I'm going to name, say, this one, or sorry, react it, and I'll redraw that one. And so I'm going to draw the bromine here like this. So 2 different compounds essentially that can come out of it. 1, 2, 3 carbons. The bromine starting on the one side here, so that's a 1, 2, 3. In this case here, if I start from this side, 1, 2, 3, so 1, 2, 3, or the other side, 1, 2, 3. It doesn't matter, this bromine's always in the 2 position. So I'm going to erase this one here. And so I've got in this case here, a 1-bromo propane. And that's all one word, no space. And in the other case, I have a 2-bromo propane. All one word, no space. So we'll try the next one here. Recognize that this is an alkene, so it's a reaction of an alkene, and I'm reacting it with this compound. So I'm going to try to find it somewhere in the literature and see if we can answer this question. So under the first page of reactions of alkenes, it gives a generic summary of the types of reactions that can occur with alkenes. So you can find something similar. It's not the exact reaction that we're looking for, but right here is very similar to what we're looking for. So we've got HBr being added. X is a halogen, so it's either HCl, HBr, or HI. Note that HF is not really ever used because in the alkene it can be used, but for most reactions, a carbon fluorine bond is very strong and doesn't typically react. So usually when you see the X, it always refers to chlorine, bromine, or iodine. So there used to be a double bond here, so this is the double bond. And then when it reacts, the double bond's going to disappear, and the hydrogen is going to go on one carbon, and the halogen will go on another carbon. In this case here, it's not very selective because it's a very symmetric molecule. But note that if this methyl group wasn't there, that under these conditions, the halogen would go on the what we call the most substituted carbon, and I'm going to show you what that means in a sec. We went over it in class, but this molecule here is symmetric, so the hydrogen can either go here or the bromine here, or it could go vice versa. The bromine could go here, or the halogen could go here. It'll create the same molecule either way. So this is the reaction that we're looking at, and essentially this is going to add across a double bond. And I've got two choices, so I'm going to tell you what the answer is first to start off. So this is my six-membered ring, badly drawn. There's the methyl group that's still hanging out right here. So that's the methyl group. I got to redraw the entire molecule. The only thing is that this is where the reaction is going to occur, somewhere across this double bond. So this is where I'm going to add the H and the Br. It's going to come across this double bond. And so I've got two options for it. I've got one where I could have, there's my methyl group again. I could have the hydrogen added here, and I could have the bromine added here. Or the other option is I could have, there's my methyl group again. The other option is I could have the bromine added here, and I could have the hydrogen added here. Now there is a preference in this reaction. And so what we need to do is understand what the most substituted carbon is. And so if I take a look at the double bond here, I'll change the color here. So when I look at the double bond, I'll see that if I look at this carbon here, how many carbons are attached to it? I got 1, 2, 3 carbons attached to it. And if I look at the other double bond, the other carbon on the double bond, I've only got 1, 2 carbons attached to it. I'm going to call this a 2' carbon, and I'm going to call this one a 3' carbon. And so the most substituted carbon is the one that's going to get the halogen. So this is the one that's going to get the halogen here. And this 2' over here will not get the halogen. So this is the correct answer. This is the most, or the most produced one out of them, the major product, and this one is the minor product. Very little of this will actually be produced, and I'll show you why right now. So when this reaction occurs, I can put my H plus and Br minus like this. And essentially, I've always told you that negative attacks positive. There's an excess electron set of electrons here in the double bond, so these two electrons will actually do the attacking. So they'll come up here and hit this, and then the bond that's between these two things will come out here like this. And so what happens now is this hydrogen is either going to go on this carbon or this carbon. And now this is why we have the two choices. So I'm going to draw this hydrogen here in red. So I can either have the hydrogen here, here's the original hydrogen that was part of this over here, part of the double bond. So there's the extra hydrogen, but there's nothing here on this side right now. So there's no extra atom here on this carbon, and so this actually carries a positive charge. So if we were to go through and do a formal charge, there's a positive charge right there. And so the positive charge can be there, but if I have the hydrogen attack the other carbon, instead, then the positive charge is on the other side. And so I'm going to have my hydrogen here, I'm going to have my carbon here, and I'm going to put a different color in. and I'll have my hydrogen here. But that means I'll have a positive charge right here on this carbon. So the positive charge either wants to be on this carbon or this carbon. Again, like I said before, we're looking for the most substituted. The most substituted carbocation, we're going to call this, because it's a cation for a positive charge and it's a carbocation for carbon. Whichever is the most substituted is going to be the most stable, meaning it's going to last a lot longer. It's going to sit around and be able to react. So the most stable compound, intermediate of these, will actually be the one that produces the final product. So again, I'm going to count the carbons that are attached on each of these. And so what we're going to do is see that if I look at this carbon, I have 1, 2, 3 carbons attached. This is a 3' carbon. And here I've got 1, 2 carbons attached. This is a 2' carbon. So this is the one that would be preferred overall because it's more stable. It's going to sit around in solution longer and hang around. And because I have this bromine minus sitting around in solution, and look, it has a minus charge on it, it's going to come in and attack. So it's now, the bromine now is going to come in and attack this negative charge, and that's why the bromine essentially is going to be situated here like this on this atom here like that, and that'll be the final answer. This will be the major product, and this is going to be a minor product. Very little of this is going to get made overall. So I'm going to show you now why the stability increases in order like that. So let's say I have a compound here. I have a central carbon and 1 hydrogen attached to it. And I got a carbon up here with 3 hydrogens coming off. That's a methyl group, another methyl group, and another methyl group. So if I were to say that I've got a carbon here, that means I have 1, 2, 3 carbons attached. So this is a tertiary carbon. What I'm going to do is I'm going to remove this hydrogen and I'm going to take the electrons with it, and I'm going to leave a positive charge here. So what I'm going to do is I'm going to redraw this molecule a couple of times with different scenarios. The first scenario being I've got 1, 2, 3 methyl groups, 3 carbons attached. The next one's going to be 1, 2 carbons attached, 2 methyl groups, and 1 more hydrogen down here. So that makes it a 1 secondary carbon. And then I'm going to draw another one where I've got 1 methyl group, 1 carbon up here, a hydrogen and another hydrogen. So that means only 1 carbon's attached as a primary carbocation. And I'll do one where I've got 3 hydrogens. So that's just a methyl carbocation. So there we go. I've drawn them out. So again, because I have the 1, 2, 3 carbons attached to this, this would be considered a tertiary carbocation. So that's this one here. If I were to remove this hydrogen, including the electrons, if it went with the hydrogen, there's no extra electrons here, so it would carry a positive charge at this carbon. So there we go. There's a positive charge right here. If I were to have this instead of a methyl group here, I had a hydrogen. This has got 1, 2 carbons attached. So this is the tertiary. This is a secondary carbocation. This carbon right here, which has the carbocation, has 1 methyl group attached, 1 carbon. And so finally this one here, which I'm just going to put M for methyl. But this is a methyl carbocation. And so the stability comes from the fact that this is a positive charge and it needs something negative around it. Well, technically there's nothing negative around it except for all the electrons. So the more electrons that are associated in this molecule, eventually they're going to come and help out with that charge. The less the less electrons that I've got, then the less likely it's going to happen. So use my cursor here and actually show. So I've got a carbon here which has a number of electrons plus the 3 hydrogens, a carbon plus the 3 electrons, carbon plus the 3 electrons. So all of these electrons are floating around the molecule, just going around, whizzing all over the place like this, and eventually they start to help stabilize, more so than this one, which has less electrons because it only has a hydrogen. It's missing 2 other hydrogens plus a carbon, all the associated electrons. So this has less electrons to help stabilize. This has even less electrons, and this has the least number of electrons to help stabilize this positive charge. So what happens then is that the tertiary carbocation is more stable than the secondary, more stable than the primary, more stable than the methyl. And so it's this order that helps dictate what happens when we start to see things that are called additions to double bonds and creation of double bonds as well themselves. So in the addition to double bonds, we're going to learn something called the Markovnikov and the anti-Markovnikov addition. When I add the alkyl halide to the most stable carbocation, that's going to be called the Markovnikov addition. When I add the halogen to the least stable carbon, that's going to be called the anti-Markovnikov. I'll just put AM, but the anti-Markovnikov addition. And we're going to see examples of that soon. So looking at our product then again, the bromine is added to the most substituted carbon, so this is a Markovnikov, that's supposed to be an M, Markovnikov product. So this is a Markovnikov, that's a V, addition to the product. One thing we didn't do is we didn't name this, so this is a cyclohexane. In the one position is a bromo, and in the one position is a methyl, and since it goes alphabetical, they're equivalent, the alkane and the alkyl halide. We're going to go 1 bromo dash 1 methyl cyclohexane. Sure hope I spelled that right. There's no spaces in this, and there's a dash between the 1 and the B, and a dash between the 1 and the O, and there should be one right here between the 1 and the M as well. No spaces at all in this, and that's what you would type in as your answer. So we'll try the next one here. What I wanted to point out, again, reaction of an alkene. We got some fancy reagent up here, but I just want to skip down here and just note the difference. So see this one here has a 1 in front and a 2 in front, and this one does not. Yet the reagents are exactly the same, other than the fact that this is a hydroxide ion. So it pretty much tells you that any counter ion could be here. It could be lithium, sodium, or potassium. This one specifies it. But overall, though, this is the exact same reaction as this one. Sometimes they specify the 1 and 2, sometimes they do not. Sometimes they tell you the counter ion here, sometimes they don't. But sodium is a spectator ion, as is lithium and potassium, so they really don't play a role at all in the reaction. It's the hydroxide ion, which is the base. That's the thing that actually does the reaction. So that's the thing to pay attention to. You'll sometimes not see the spectator ion involved in the reaction at all, and just note that there is something there. So we'll continue on with this one, and we'll try to find, under reactions of alkenes, we'll try to find this reagent. So as it turns out, on page 16 of our notes that we've got, we'll find this reaction. There's a double bond, there's BH3THF. It tells us it goes through this intermediate, and then eventually we add a second step to it, which has got the peroxide and the hydroxide ion, and we finally end up with, this was the double bond. The hydrogen adds to one carbon, and the hydroxide adds to the other. But what you need to note here is how it adds. It actually tells you it's in the anti-Markovnikov addition. So that tells us this hydroxide ion, if I have a choice between a secondary and a tertiary position, it will accept the tertiary, the least substituted one, the least stable. So what this BH2 does is it actually kind of goes on to the most stable one first, and it exposes the other one so that the hydroxide comes in and attacks it. So that's what happens essentially, is this thing tricks the compound, the hydroxide, into attacking the least substituted carbon instead. So that's what happens with the anti-Markovnikov. Another example is the cyclohexene group, and so there's the most substituted carbon right there. There's the least substituted. We know that there's going to be an addition across this, that a hydrogen is going to occur on one side, a hydroxide on the other, but because it's anti-Markovnikov, this is the most substituted carbon. This will not get the hydroxide. This one will. And so the hydroxide should be coming off this side and the hydrogen here. And so that's what they show. They've expanded all the hydrogens involved. There was the double bond. These two carbons are involved. Something's going to happen to them. One's going to get the hydrogen. One's going to get the hydroxide ion on it. And this is the final compound. So we're going to apply this to the compound that we've got. So when we look at the reaction then, there's our double bond. Essentially we've got this is carbon right here. This carbon right here is going to go through the reaction. And so what we realize then is that since it's this special reagent here, that it's going to be an anti-Markovnikov addition. So that meaning that this hydroxide is going to get added on, it's going to come onto this carbon here, and the hydrogen is going to get added on. So what I've drawn here is actually incorrect, and we'll redraw the correct one. So redrawn, this is a tertiary carbon, and since it's anti-Markovnikov, the hydroxyl will not go here. The hydroxyl will go here. And so this is the secondary carbon, the least substituted. The alcohol goes on this position. So now if I were to name this, I could start from here and go 1, 2, 3, 4, 5. Or I could start from this side, 1, 2, 3, 4, 5. Either way, the hydroxyl group, which is highest priority, is in the 3 position. So what that means then is that I have to start from this side because I want to have the least number on any substituent. I still have this methyl group hanging off here. So if I draw something around this like this, this methyl group is still hanging off and I still need to name this. So to start to name this then, I'm going to recognize that this is a pentane with the 5 carbons. In the 3 position is a hydroxy, but it's an alcohol, so I'm going to put OL because it's highest priority. And that means that I got to change this E to an OL. So I can either call it a 3 pentanol, and then the methyl group goes in front. So in the 2 position is the methyl, so I got a 2 methyl dash 3 pentanol. Or the other one, which is my preference, is I would say 2-methyl, it's supposed to be an L there, pentan 3-all. Just get used to burying that number inside so that it actually, for more complicated molecules, it helps you out.